All right. Good afternoon. Wonderful to be having a great time here at Percona. This is my first time actually to the North American one. I went to the one in Frankfurt a couple years ago and really enjoyed it. But for some reason, this is my first time to Percona in the United States. I'm getting to speak 4 times, so it's a little exciting. My name is Bruce Momjian. I work for EDB, and I'm one of the Postgres core team members. This talk is an interesting one because it tries to outline how Postgres is unique in the data landscape because it's got a number of features that have allowed it to be changed to meet the more modern needs of enterprises. The slides are actually at this URL right down here. So if you want to download the slides or you want to watch a recording of the slides, there are 58 presentations there, 98 recordings last I looked. There's also 640 blog entries categorized, so a lot of information if that's what you're interested in. We're going to be talking about 4 basic trends in the history of Postgres and basic ways that Postgres meets today's data needs. The actual things that make Postgres unique actually date back to 1986, which is kind of crazy old, but somebody had some real vision at that point, and I'll be talking about that. We're going to talk about how Postgres handles NoSQL needs. I did speak about that this morning in my non-relational Postgres talk. Then we're also going to talk about how Postgres does data analytics. This is another aspect of relational systems where you do data analytics inside the same database as you're doing OLTP. That's a major trend. People would rather not have separate data warehouses to do data analytics. And Postgres meets that need in a lot of ways. And then finally, database federation. We'll talk about foreign data wrappers and how Postgres interoperates with other systems. And finally, how Postgres has a central role potentially in your data center. Let's talk about object-relational Postgres, really designed in the 80s. And it has an extendibility concept that was originally designed, not added later, but originally designed that way, that allows for object-relational concepts like inheritance, database-defined objects that are easily manipulated. Here's a slide I think sort of illustrates that behavior. You can see these are the Postgres system tables. You can see the normal tables that you're probably familiar with, like the PG class, which holds the names of the tables, PG attribute holds the names of the columns. But then you have some unusual ones like the PG type table, which holds the types, the data types that are defined in Postgres, both the custom ones and the standard ones. PG proc for stored functions, PG operator for all of the operators, like the plus sign and minus sign. All the blue over here are the indexing methods, btree, hash, gin, gist, spgist, and brin. Here are all the aggregates that we define, the triggers, and over here are some things related to inheritance and statistics. The point is that with Postgres, you don't have baked in, or the types are not predefined in the binary. They're actually defined in these system tables. And what that allows you to do is to effectively make changes to Postgres in ways that will change the way it behaves. And again, this was originally developed long ago, but now has become relevant as data needs have changed for modern applications. Here's an example of a data type that I'm installing. I basically install something called extension called ISN. So I type here in red, create extension ISN, and basically I now have 8 new data types that didn't exist before. These are related to book numbers, magazine numbers, and music numbers. Also, there's a UPC code that is validated to be a valid UPC code. Now, one of the unusual things about Postgres, and again back to the extendibility concept, is that there's no real difference between the standard data types like an integer or varchar, and the custom data types that we just loaded. So for example, here I'm running a little list to show me the different data types. You can see the top one's an integer, it's normal, and then the bottom one is a book number, and that looks just like effectively the integer one. In fact, if we look at the system tables, we can see that the integer internally is labeled as int4, and you can see in red here the various input-output functions that represent int4. You can see that int4 is defined as being 4 bytes long. It's passed by value. Let's see here, what else can we look at? So these are basically the things that make an integer, is the length and the input-output functions are probably the two most characteristic ones that identify what makes an integer. And if I look at the ISBN data type, which is the one I just added, it looks very similar. It's an 8-byte wide field, not 4, and it has different input-output functions, and that's what makes it a book number. So the point here is that the book number and the integer, which are effectively both data types in Postgres, are defined in pretty much the same way, and they behave almost identically in terms of how they list, in what capabilities are there, and what indexing capabilities are there. It works really, really well. So that's kind of interesting, because Postgres had that extendability originally developed at Berkeley in 1986. That extendability basically lied dormant, I'd say, for the first 20 years or 15 years of Postgres. But what we've seen in the past 10 years is a huge explosion, either whether it's PostGIS or JSON or full-text search or range types, where we've been modifying Postgres to meet the data needs of today's industry. And because of Postgres' extendability, it's been really easy for us to make those modifications. Here's another extendability option. It's called PL-Python-U. It's basically an untrusted procedure language written in Python. It allows stored procedures in Python. You can see the built-in one, PL-PGSQL, is built in, and it looks exactly the same as the PL-Python one. It lists the same, it behaves the same. Obviously, one's in Python and one isn't, but they have the same access to the same facilities in the system. In fact, we allow for all of these procedures, stored procedure languages. This whole stored procedure API is generic. So we have PL Java, which is not used very much anymore, but it's still around. PL Perl is very popular, particularly because there's a trusted version of PL Perl that allows non-super users to write stored procedures. PL PGSQL, super popular. PL Python, super popular. PLR for analytics. PLSH if you're running stuff in shell script. PL V8, that is obviously a JavaScript engine, and we even have a C server-side language. So really a lot of extendability here. You only, by default, Postgres really only has the bottom one, the SPI, and the PL PGSQL. You can compile Perl into Postgres, you can compile Python into Postgres, and then some of these, like PLR, are separate projects that you would download and install and then load into whatever database you want. So again, that extendability follows to stored procedure languages. Specialized indexing methods, you see the standard ones like btree and hash, but we have others. So we have gin and gist and spgist. I did talk about those this morning in my non-relational talk, and those are really good for non-relational data. So things like full-text search, JSON, range types, geometric types, all really need those specialized indexing. Because if not, btree is great for linear data, but anytime you're doing nonlinear data, whether it's a two-dimensional point or something like a JSON or full-text search, there's a lot of different keys inside the field. Something like a gin or spgist is really the way to go. And if you don't have those, your system really isn't going to be a fully functional non-relational system. You might think that that list was just kind of made up, but in fact, we even defined the index types in the system catalog. So here's a query from the PG_AM system table, which basically shows that we have what is that, 6 stored procedure languages built into Postgres. And that's that yellow area I showed you on the previous slide where I said these were all the system tables where we define indexes. We actually define them this way. So if we were to add a new indexing method at some point, somebody would write the indexing method, and they would hook it into the system tables, and then it would become available to the rest of the system. We have operators are flexible. This is something you probably don't think of as being a flexibility requirement, but if you're going to allow for custom data types, you're going to need to have custom operators potentially for those data types. So something like a plus sign is effectively defined as a function call with 2 integers on either side. So int4pl is int4 plus, and there it takes 2 integers on either side. So if you wanted to add a new operator that did something special, you would basically write the C code for that and then define those, do create operator at the SQL level to install that operator in the current database. And then you would be able to use that operator in your own queries for your own special data types. Or you may want to add an operator to an existing data type. That works too. We also have aggregates that are defined in the system tables, like sum, count, and so forth, in the PG aggregate table. So we could potentially define our own aggregates, casting from one data type to another. That's stored in the PG cast table. We do have a number of people who are now using the extension system for Postgres. So PostGIS is probably our most popular extension. It is used for geographic information system. So Postgres supports a number of geometric types like point, circle, box, polygon in standard Postgres, but PostGIS really takes it to a next level where you're able to effectively take the entire GIS system, which is basically different mapping coordinates for the globe, and then do distance calculations, do recording of land use and so forth. A very, very sophisticated system, is developed completely independent of Postgres, but basically just loads right on top of Postgres. PLv8, a server-side language, I mentioned that one earlier. That is, again, a separate project. And a lot of our current capabilities, like full-text search, which were originally developed for externally, and then once they were proven out, they were moved into the main part of Postgres. But of course, they're still defined in the system tables and so forth. We have a lot of offshoots of the Postgres source code. So, in fact, there's a bunch of them. We just had one 2 days ago. Google now has a custom version of Postgres. Google Cloud has a custom version of Postgres that they're now supporting. Similar to Amazon Aurora or Azure Postgres or Alibaba's Postgres, where they are basically modifying Postgres to use a customized storage layer. So unfortunately, that's not on the list. I got to add that one. But things like Greenplum have been around for years. They're an offshoot of Postgres, are now trying to move back to current releases of Community Postgres. I'm not sure where that is. Netezza is an offshoot of Postgres, particularly for, I think, specialized hardware that does really complex filtering at the storage layer. That was sort of their claim to fame. Amazon Redshift is based on Postgres. Vertic was based on that as well. I got to get the Google one in there now that they've created it. But the point is there are a lot of offshoots. In fact, this is a chart of all of the offshoots that we have. And as you can see, we got some exotic forks. We have some window ports, although that is not as popular anymore because Postgres community has had a Windows port for now 10, 15 years. There are a number of clustering and distributed database versions out there. I think, I'm trying to think of the big names. Cockroach is a big one. There's a bunch of them out there doing distributed Postgres, and it's kind of interesting because the Postgres source code is easy to use, and they're basically using it to kind of go into new areas of data science, which I think is really cool. We also have obviously some big data ones like Greenplum and Vertica that were offshoots of Postgres. This slide's a little older. I'd love to have a new version. It stops, as you can see, in 2015. But the point is that there's just a huge explosion. Yugabyte's another one in the distributed space you see a lot. So it's kind of interesting how Postgres is kind of moving in that direction. And the source code is so good that people are very happy to be basically creating new versions of it and to handle new workloads. So basically with Postgres, plugin's not a bad word. It's not something you have to avoid. Postgres, effectively, even our native data types and our native indexing is plugged in a way because they're all defined in the system table. So a plugin can the reason this is I had to say this is because a lot of systems, when you hear plugin, particularly in the database space, you think, oh, it's not going to work right, it's not going to back up right, it's not going to have the right transaction semantics, the optimizer's not going to know about it, it's not going to, replication's going to be a problem. There's going to be something that doesn't work. And the reason is because adding extendability to an existing system is really hard, unless you catch all of the spots. And that's really difficult to do, particularly if you're not willing to re-architect the whole thing to properly handle it. And that's why a lot of systems that have had extensions that do special things have all these limitations of what they can do. And that's not true of Postgres because it was originally designed to be extendable. And for that reason, the extendability is a first-class citizen, and it's not something you have to be sort of wary of or worried that there'd be these surprises later. That really just doesn't happen. Okay? So again, you have some parts of the system which are internal here on the left, and then you have some of these extensions here on the right that can be added in, and once they're added in, they behave just like the rest of the system. So let's look at a particular extendability example, and this is the NoSQL space. Now, as you know, NoSQL kind of was the big thing maybe 8 or 9 years ago. There's a huge hype around Mongo and Cassandra and Hadoop, but there's just a lot of stuff going on at the NoSQL space. That's kind of quieted down now. There's been sort of a consolidation. You don't see as many NoSQL solutions. I think people are a little more, a little wiser about where NoSQL makes sense and where it really doesn't. Having been in relational systems as long as I have, there's always been this sort of doom and gloom that relational systems, because they started in 1970 with EF-COD, they're like, well, maybe the relational here is over, right? Maybe we don't need to do relational anymore. It's old technology. It was designed for a different use case. And we really need to move to a completely different development storage paradigm. However, this is not the first time that relationals had challenges. We've had challenges from object databases in the 90s, from XML databases after that. But what's typically happened during that period is that relational existed, some new technology showed up, whether it was an XML database or object database or whatever, and over time, people are saying, oh, relational is dead. We're going to be using only XML databases now. Well, it's kind of crazy to say it now, but that's what they said at the time. But what typically happens with relational technology, because the relational sort of structure is so flexible and so powerful, that the challenger basically has some capability that relational can't do, and relational finds a way of taking that relational, that capability, and bringing it into relational. So for example, we can store XML now, right? We can do sort of object style storage now. So the concept of of, oh, you got to get rid of relational because you need feature X. Well, feature X just kind of moves into relational, and relational just keeps going. And I think the NoSQL example is a good case for that. So, NoSQL it's like this big umbrella, but it's like a negative umbrella, right? Because it's really a non-SQL. So we don't say what we are, we say what we're not. And obviously anything that defines itself as what they're not really isn't defining itself as what they are. In fact, there's 4 different types of NoSQL. There's the key value store, which would be a standard Redis. We have the document database, which would be like a Mongo, which would store JSON. We have Cassandra, which is a columnar store, really good for storing non-relational data that has a lot of duplication. And also graph databases like Neo4j, which is looking mostly for relationships between values in the same table, which is not something you can do it relational. Actually, we actually do it really well. But there's a case where people would say, oh, I would need to do a lot of relationships of one row to another row in the same table. I need Neo4j. No, well, maybe you do, but Postgres has common table expressions, which actually work really well. We've had some, at EDB, we've done a little benchmarking on that. And you take a standard graph database benchmark, you run it against Postgres using common table expressions, it actually has really good performance. So again, same thing with Mongo. We thought Mongo was going to be super fast. We actually contracted out for some third party to do some benchmarking of Mongo against Postgres, our company EDB, and we found that in most cases, Postgres was faster. Even though Postgres had a relational model, even though Postgres did much more than JSON, it's kind of weird. You think if Mongo just does JSON, it would always be faster, but it wasn't true. And probably similar sometimes for graph databases as well. So again, that concept of relational kind of pulling out the features of other competitors and then making them their own is not new and something I think has happened and is happening in the NoSQL space. Why does NoSQL exist? And this is, I think, something that's not very clear to people. NoSQL was really optimized for a very specific use case. Auto sharding, very simple queries that have to be super fast and flexible schemas. The bottom line, though, is that most people who are running NoSQL are not using auto sharding. They're just running a single host. Or if they're running 2 servers, the second server is only there for backup. What NoSQL really was designed for was shared nothing, distributed, 10 servers, 100 servers, all kind of spread around. Because you've ripped out all of the relational capabilities, joins and constraints and transaction control and unified backup. And so you ripped out all that. You better get a pretty good value if you're going to rip out all that stuff. And unfortunately, a lot of people, I think, didn't understand that. They sort of bought the NoSQL Kool-Aid, as they say, and they threw out the relational benefits, and they got these 3 benefits that I'm showing you here. But if they aren't using the sharding part, like, is there really a value to throwing out all that relational capability? And a lot of people are sort of saying no. If you look 5 years ago versus today, where people are doing deployments, there's a lot more hesitancy to go the NoSQL route because of that additional cost. And again, if you don't need the auto sharding, is that really where you want to be going? When you do NoSQL, you lose a powerful query language. You've got to do a lot more in your application. You've got to do analytics in your application. You've got to do transaction control in your application. You've got to do joins in your application. Constraints have to be done in the application. A lot more work. You lose the sophisticated optimizer that you have. Normalization, joins, data integrity, durability, all these things kind of go away. And if you're going to throw out all these things, you better get a good value out of it. And a lot of times people weren't getting that. So is it worth the cost, right? NoSQL makes reporting difficult. Applications are complex. And durability is something you have to be careful of. So I'm not saying NoSQL never makes sense, but you have to make sure that what you're giving up is worth doing that. When should NoSQL be used? Primarily, I would say massive write scaling, something much more than a single server can provide. Now, we're working with Postgres on a sharding solution. We have the rudimentaries of that in Postgres 14 and even more in Postgres 15. So I think we're coming to, again, subsume that massive write workload into Postgres. But right now, or at least historically, a massive write would be a good reason to use a NoSQL solution. Very simple data access pattern. Again, something doesn't really need a sophisticated query language would make sense. If you're willing to spend more for development, because developing on a NoSQL may be easy at the beginning, but once you start to bring reporting in and the life cycle of the application that now has to deal with different data formats that were written at different times and without any kind of normalization or data integrity, you're going to spend more overall for application development. Data retention and transaction control, again, not guaranteed. You've got to make sure you get that right or figure out how to fix it. And also, if you're using unstructured duplicate data that benefits from column compression, that's where a columnar database would really make sense. And I can't say that Postgres really has a great solution now for that workload. Relational, obviously, great for administration, great for variable workloads and reporting, simplifies application development, and obviously has strong data retention capabilities that are almost unmatched in the industry. What's great with Postgres is you can, in some sense, get the best of both worlds. You can do schema-less things with things like JSON. It has sophisticated indexing, which is what I talked about this morning. We have transactional schema changes. I'll show you that and how that works. It's pretty cool. And of course, you have durability. But that durability can be controlled. So you can reduce durability if it's not necessary. Postgres docs go into clear explanation of exactly how you can control that durability there. So here's an example using JSON-B. If you were in my talk this morning, that's example pretty much the same as I talked about. We create a specific JSON-B column. We can now load a JSON-B document into our system. And now we can actually run a query and say select the value of the name key where the age key's value equals 21. And as you can see, Bill was listed as 21 here. So in fact, it does return Bill. There's a lot more functions here I can't talk about. I think we have 100 different functions. I was surprised at how many we have that work on JSON. So there's an entire boatload of stuff. And Postgres 15 coming out in September, October has even more JSON capabilities, particularly a lot of compatibility around SQL, the SQL JSON standard. So that's really exciting. In terms of schema changes, Postgres allows you to do schema changes inside of a transaction block. This is something that a lot of relational systems can't do. So we have the capability here of, in this example, adding 2 columns and renaming the actual table inside of a transaction. And the beauty of this is that the other sessions on the system will not see intermediate changes. They'll either see the old table as it existed up here or the new table as it existed up here. But this will be atomic. If any of these fail, it will auto roll back. And once you commit any new transactions, we'll automatically see the new structure for that table. So that is an example of flexible schema changes. I know it's not sort of as sort of super flexible as JSON, right? And we have JSON and JSON-B for that. But if you don't need something super flexible like that, and you want to stay with relational columns and relational storage, but you need to update your schema occasionally, Postgres is a great option for that. So I've talked about Postgres extendability and basically how Postgres got to be extendable and a lot of the growth that we've seen in extendable workloads. Then I talked about NoSQL. In this section, I want to talk about data analytics. Data analytics, obviously, is the analysis of data that is in your system. but on a massive scale, not like look up 2 records, but look up millions of records and do some type of analysis on them. Historically, data analytics was done in a separate system. So you'd buy a separate server that just did data analytics, and then you'd copy your data over from your relational system to your data analytics system, and then you'd run analysis on it. The problem with that is that you really had to have these batch jobs, which are moving data, mass amounts of data over all the time. You had to keep it synchronized. If you change the schema over here, you had to change the schema over here. And it had to be done in batch, so it would be at night. And then when you ran your analytics weren't really current because they were whatever was current at the time you dumped your data. So that's really not ideal. What you see a lot now is people doing data analytics inside of Postgres. So a lot more focus on people wanting to do data analytics inside the same database that they're doing their OLTP workloads. So fortunately, Postgres has the standard SQL capabilities like aggregates and a powerful optimizer. But and window functions. We have some unusual things like PLR, which is a server-side language we talked about earlier. But PLR is specifically designed for data analysis and data visualization. That, if you're doing data analytics, I definitely recommend that. We have standard things like data partitioning, materialized views, table spaces, common table expressions. We have Brin indexes. I talked about that earlier as a specialized way of doing data warehousing. We have a just-in-time compiler, which is designed to help the executor to basically process large volumes of rows in parallel. Large rows efficiently. We have parallelism, and then we also have sharding, as I said before, in progress, that every year it gets a little closer. And I think that's also a key aspect of data analytics. Now, you might say, well, I don't want to run analytics in the same server as my primary database, and you don't have to. You can basically have a primary database. Here we have on the left, which is doing my OLTP workload. And I can use binary replication to create a read-only replica here on the right. And I can send all of my data analytics queries into my data warehouse. I can do all my analytics workload there. I could have 20 of them if I wanted to. And therefore, I'm getting fresh data because replication is basically updating the data live. But at the same time, it does not impact the performance of my primary server, which, of course, is doing my OLTP workload. So that's, I think, a great use of analytics for Postgres. And finally, database federation. Obviously, we'd love all your database data to be in Postgres, but that's not realistic, right? People have Oracle out there. They've got Mongo out there. Maybe they have some Redis or MySQL. And the nice thing about Postgres is that it has something called foreign data wrappers, which is part of the SQL Med standard, which I used to think medical, but it's not. It's management of external data. And the SQL Med standard effectively gives a standard for implementing or joining to other data. Postgres actually supports over 100 different foreign data wrapper sources. So you can have Postgres connecting to all of these different sources, either read or read-write, and effectively giving you a federated solution. So these are some of the relational systems we connect to. These are some of the basically interfaces that we would connect to. So anything that does JDBC or ODBC, we can connect to. We also do things like files and HTTP requests. We can get data out of Amazon S3. We can do Twitter. I think Twitter's read-only, fortunately, but it's out there. So how do you do it? Here's an example of just a really simple one Postgres server to another. You create a server. You specify the IP address. In this case, it's a localhost connection and the database name. We create a user mapping, which is effectively my authentication. And then I create something called a foreign table. And this foreign table is basically will look like a table on my local system, but in fact, it connects to the world table on this foreign server. So now I can actually do queries against the world table, and this world table will effectively run the query on the remote system and bring it back. It's very sophisticated. It will push down where clauses and joins and sorts to that foreign system. Aggregates will be pushed down. So it's really, it isn't just send a blind query out and pull all the data back. It's trying to have as much data, as much work done on the remote system as possible to limit the impact on the system that's sending it. And this capability has been around for years. Super, super useful. So here's an example of effectively Postgres connecting to an Oracle database, a Mongo database, and then a Twitter feed. And you basically have 3 tables that look like tables inside of Postgres, but are in fact foreign sources. And I think that's very powerful. So what am I really getting at? We've talked about NoSQL, we talked about extendability, we talked about data warehouse, we talked about foreign data wrappers. What I'm really trying to get to is the concept that Postgres has a unique role now as sort of a central data broker within organizations. It is probably the only database that has the object-relational flexibility and extendability that can do NoSQL workloads with indexing support to make those fast, that can do data analytics inside of Postgres, and also can access over 100 different data sources. No other database really has all of those capabilities. So when I think of effectively where Postgres fits within an enterprise, I think as time goes forward, the concept of Postgres being having this central role within organizations is going to get more and more important, because it's really the only database that can do the NoSQL workloads and the specialized extension workloads and the data warehouse workloads, and allow you to integrate that with all of the other data sources within your organization and sort of bring those together. We're definitely at a polyglot database world where people are bringing in a whole bunch of different databases at once. But the problem for organizations is, how do you bring those together? How do you make that data work together? And I think Postgres is an ideal position to sort of bring that together and give organizations sort of a central place to kind of hang them all together and keep them so that those data sources don't become data silos that effectively can't be queried or can't be made to work to further the goals of the enterprise. So that is all I have to say. I would be glad to take questions if anyone has any. If yes? You do? Okay. Yes, sir. I got good news for you. Okay, so I've been working on sharding for about 5 years. So the question is, where are we with sharding? Been working with sharding for 5 years. My website that I listed down here at the bottom has a presentation about sharding. Okay, so that would be the first place I would probably look. It also has links to other places from that presentation that you can look at. The good news is that in Postgres 14, we added the final piece that was really going to be necessary to do read-only sharding. And that is the ability to scan foreign data wrappers in parallel. And that was done in September or October of last year. Unfortunately, I haven't had anybody benchmark it. Like, I haven't found anybody who really wants to put it to work and tell me how well does this work or how well does this not work. So I'm looking for somebody to actually do that. So as you can see from the presentation and what I talked about, what we've needed to do was to get, like, if you look at the way Greenplum did it, they just took Postgres and they just like ripped out a whole bunch of stuff and just put a whole bunch of stuff in, and they've got data warehousing. But the problem was it was only doing data warehousing, and then if they wanted to keep up with Postgres, they had to like whack it around. And they've had great trouble keeping up with where we are. And I think they went to Postgres 12, and I think they stopped there. So I don't know what's going on there. The bottom line is, if we want to do sharding, same thing with transparent data encryption, which is another key aspect people want, it's got to be organic. So we basically grew partitioning. We grew parallelism. We grew foreign data wrappers. We got foreign data wrappers to push the joins and the where clauses and the sorts and the aggregates down to the foreign servers. So when you're doing a read-only data warehouse with Postgres, you're going to scan the partitions in parallel. The aggregates are going to get pushed down. The where clauses, the joins, all of those get pushed down. The data is going to come back. Postgres knows how to combine those results together as though it would normally do just for a standard partition table and return the result to the user. So the good news, I think we're in good shape with the read-only part, where I think we did some improvements in Postgres 15, which is coming out September, October, is the read-write workload. So allowing for commits across multiple servers in parallel. So if you look at the release notes, and I put out a blog entry on Monday about the release notes that we just finished for Postgres 15. If you go down, look for foreign data wrappers in Postgres, you'll see there's a number of fixes that don't look really exciting, but in fact they're there to allow us to do the read-write sharding, which I think is super important. But again, read-write is a little more complicated because we have to make sure that we're doing prepared transactions across all of the shards, and because you know what I'm saying, we can't commit on some and not others. So one of the keys I remember was parallel prepared transactions on a shard. And you're looking like, why is that important? Well, when you look at it alone, it doesn't make sense. When you think of the sharding workload, it actually is very important.
So you've been working on 5 years, and are you saying PG-15?
So yeah, we've been working for 5 years. I think we're ready for read-only testing now for data warehouse. I've talked to EDB about it. I can't get them excited. I talk to people about it. Someday somebody's going to get excited about it and actually put together a benchmark and tell us how it performs. But we're not stopping there. We know we have to do the read-write part, particularly for the write-heavy workloads, which is what I talked about. People were using NoSQL for write-heavy workloads. We can fix that with read-write sharding. But for read-write sharding, we need that prepared commit capability across shards. And we also need a snapshot synchronization across shards. And that, I think, is going to come from someone else. And I haven't seen, we have some patches on that. So I think we're still, the read-write part, I'd say we're still 2 years away. Yeah, but I'd love to see the read workload. And I think some read-write workloads will work now, particularly with Postgres 15, because we've been targeting. And the Chinese actually have done a lot of work here. For some reason, China, because of their high data volumes, has been much more keen on, and in some sense the Russians, but even more the Chinese, have been much more keen on this. And there's a company called Hygo, which has been, and some of the Japanese guys as well, have been sort of really doing some amazing work in here. And sometimes it kind of is invisible, you know, because it takes so many years. It doesn't come as one big feature. It's like incremental. Yeah.
I got the presentation from your website.
Great. Thank you. All right. I think we're done. I appreciate it. And have a good day.